Hello and welcome to the second session of CG5042. Um, in this lecture, we're going to be looking at reliability of mechanical systems. And the whole idea here is to follow on from the design process stuff that we were covering in the previous lecture and start considering reliability and how that influences the design decisions that you may be making. Now, reliability itself is a huge field. So really what we're doing in this lecture is we're giving a snapshot of the underlying principles of it. So it's really an awareness video rather than a detailed study of reliability. And really what we want to cover are these topics here. So we want to look at definitions of reliability, what are meant, and there's kind of 5 definitions that are important to us. We look at the different probability distributions, follow this with the bathtub curve of hazard rate, which won't mean much to you at the moment, but it's quite a useful way of understanding how reliability links to the design process. And then load strength analysis and the safety margins. So in this first lecture on reliability, I'm going to really cover the first 2 topics because I want to keep the time down to about 15 minutes or so. And then in the second lecture on reliability, we will cover the last 3 points there. There's a textbook on this, which is quite good. So if you can get access to it, that's excellent. If you can't, don't worry about it. You will have enough in the lecture slides here and with my commentary, hopefully, to see you through. So just before we start, it's worthwhile just taking a note on prediction. And there's a quote here from Niels Bohr. And he's talking here about how difficult prediction is, especially about the future. And if you digest that, like a lot of what we deal with in engineering is about predicting the behavior of systems. And for things that are well described, where we have complete sets of differential equations, there's a well understood theory that is quite mature that can be used to predict future performance of these systems. That alone is very, very difficult when we know what the result is. But when we don't know what the result is, when it's in the future, it becomes incredibly difficult. And reliability really is concerned with that. And what we're moving to now is really a stochastic system. So most engineers are very comfortable with deterministic systems where things are predictable. They follow governing behavior. Whereas reliability is associated with random events. So the language is a little bit different to what engineers are usually used to. So with that in mind, we just want to get some definitions across. And these are the definitions that underpin the whole treatment of reliability in an engineering design context. So what do we mean by reliability? Well, it is a probability. So that's what I meant there about being a stochastic rather than deterministic parameter. So it is the probability that an item operating under stated conditions will survive for a stated period of time. And this condition here, stated conditions, is very important because that is linked to your specifications and it's giving you context for the total physical environment, which includes the mechanical, the thermal, the electrical, all the environmental considerations that the design must operate under. So it sort of sets the envelope under which you give warranty to your design in that sense. So many of you will have mobile devices, and these have built-in accelerometers, which are very, very nice. They're used to give you lots of information and link with apps and stuff like that. What they also do is they give the manufacturers a lot of data, and data on how you're treating the phone. So if you try and make a warranty claim on your phone, and they look at it and they see that there's quite a lot of impacts on it that they'll get from the accelerometer data, you may well find that you've operated your phone outside the stated conditions and your warranty is null and void. So this is kind of gives a context for the conditions under which the design is expected to work. Now, so mathematically, we can express that verb of words in a very concise way. So we have the number surviving at time t divided by the number at the start. So it's normalized against the number at the start. If we look then at, hopefully it'll work. Yep. If we look at failure, then is the probability that an item that was operating at the start under the stated conditions would have failed at or before a stated time t. So again, mathematically, it's the number failed by time t divided by the number at the start. So obviously, if we have the ones that are still alive and the ones that are dead, we sum to a total of 1 in terms of our population because these are normalized to the starting population. This is our first equation for reliability. It's the ROT plus FOT equals 1. And later on, we'll look at a visual representation of this that can be quite useful to understand the different terms. So an example of the kind of thing that we could do. So here we have some data on PID controllers. So you may be using them to control the valves in your process, for example, and you'd have quite a lot of them. So you want to get an understanding of the performance of these under your stated conditions. So you run a lifetime test. So here we have a sample of 15 were tested, and the first failure occurred after 1,800 hours. The second one at 3,000, etc., 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 until number 6 failed at 6,000 hours. So these are plotted on a log plot. Again, because numbers are large, logs are used because it's useful to compress the data. And we can see that it follows this trend. And we can extrapolate that trend and read off what the time to 10% of failures is, the T10. That comes out at 5,500 hours. Okay, so that's a very useful way, and it gives us a sense of determining what kind of failure rate we can expect and what kind of inventory we need to have in place to replace the PID controllers. Very useful in that context. Now, if you look at this plotting position here, you'll see that what my starting population was 50, and I got my first failure at 1,800 hours. So that is 1 over 50, which should be 2%, but it's down here at 1.4%. And likewise, if we look at this one, it's stated at 3.4, but again, we would expect it to be 4. And you can see all these numbers are a little bit off what the actual number should be. So the question is, why is that? The answer to this is quite straightforward. If you took another 50 PID controllers and you ran a lifetime test on those, you would not necessarily get the first failure at precisely 1,800 hours, and the second one at precisely 3,000 hours. So what that means is that there is a distribution associated with each failure event in the population. So what we've plotted here with the 1.4% is what is known as the median rank. And that is a way of accounting for the distribution associated with each failure event. So it's associated with the randomness of each failure event. So we correct the data using the median rank, and that better captures the distribution associated with those discrete failure events, so that when we plot it and put a fit through it, we get a more representative answer. So how do we define the median rank? The median rank is very straightforward from this formula. I is the failure number. So for example, we had number 1, our first failure. So that's I minus 0.3. So 1 minus 0.3 gives us 0.7. N is the total number of samples, in this case 50. So we have 50.4 on the bottom. So we would have 0.7 divided by 50.4, and that would give us the 1.4%. And again, if we repeat those calculations for I equals 2, we would then have 2 minus 0.3 over 50 plus 0.4. That would give us 3.4%, etc., etc., etc. for the other failure events. Now, where does this formula come from? It's just an approximation. There's quite a lot of detailed mathematics you can do. It's way beyond our scope. What this is a best approximation to that. So it is a way, if you apply this transformation to the data, it essentially gives you a value that is indicative of the median rank, very, very close to it, and you use that in your plotting. Okay, so there's three things we've covered so far. We've covered failure, reliability, and the use of the median rank. The next thing we want to look at is the PDF, the probability density function. And this is the rate of failure. Now we can do an interpretation of this. If we take f of t dt, it is the probability of failure occurring during the time interval dt when it was working at the start. Okay, and that term there is quite important because the failure rate, or the failure data, is linked to it working at the start. So in this context, the PDF is unconditional. So again, we can define it mathematically as the number failing per unit at time t divided by the number at the start. Okay, we'll see in a few minutes that there's a hazard rate, H of t, which is conditional. Okay, so that's why this is important here. So if we take a plot of the PDF, we have a life interval here based on thousands of hours. So between 0 and 10,000 hours, we had no failure. 40 to 50,000 hours, we got 30 failures. So again, we have the PDF is 0.3 there, okay, because we had 100 samples on test. Okay, we get this very, very interesting plot. Okay, and again, this is very, very useful, and it gives us indicative of the average lifespan of the stuff, the units that we are testing. So that concludes the PDF. The last parameter we want to cover is the hazard rate, H of t. And this now is conditional. Okay, so it is the instantaneous failure rate of items having survived to time t. It's defined as the number failing per unit time at time t divided by the number surviving at time t. Whereas when we looked at the PDF, it was a number failing per unit time at time t. So again, the same thing, but based on numbers at the start. Okay, so that's the difference between the conditional and the unconditional. So H of t is f of t over r of t. And if we substitute in that r of t is equal to 1 minus f of t, then f of t is 1 minus f of t. Okay, so H of t to t represents the conditional probability of failure in the time increment. So to kind of understand that a bit better, we look at this graphical overview of the terms. And this will hopefully help you understand what is meant by the different terms. So what I'm highlighting at the moment now with my red marker pointer thingy is the PDF function. Okay, so that's what we have. And if we have a time instant t star, then this value here would be our PDF function at t star. The failure data is given by the area under this curve to the left-hand side. The reliability is given by the area to the right. And the hazard rate is given by the value of f of t star here divided by the area to the right. Now, just to explain hazard rate in this context. So if we take this point here, t star, you can see that it would have the PDF as the same value as this point here. But being at this point here is much more hazardous than being over here. So let me explain that. So this area here decreases as we move along the PDF function. So what that means then is the hazard rate, H of t star, increases. So it is much more hazardous for the system to be operating at this point than it is here, because there's been quite a lot of failure and it's gone past its average lifespan. So chances are it is more likely to fail here. It's much more hazardous than it is over here. So the hazard rate is a very useful parameter to analyze. Now, in reliability, work. The objective really is to get some sort of a description of the PDF function. Okay, so we want some kind of a curve fit or generate this from data that we're able to fit a reasonable equation to it and end up with an expression for the PDF. And once we have that, we can determine then what FAT or RT or HRT are at any time point. Now, it's beyond our scope to go through the detail of that analysis, but essentially what you do is you generate data. We'll talk about that a bit more in the next lecture, how you do that. But viable analysis is used, and it's typically done in software, and you can have a 2 or 3 parameter viable analysis. Essentially what a viable function is it's a very flexible curve fit to the time data. And it gives you 2 or sometimes 3 variables to play with. So they're extraordinarily flexible under these different variables and allow you to fit a wide range of distributions. So once you're able to get that fit done, you can integrate the PDF to get the FAT, calculate the RT, or calculate the hazard rate. Okay. So the key thing that we picked up from today's lecture really is the definitions of the PDF, failure, reliability, and the hazard rate. And in the next lecture, we'll talk a bit about how you go about obtaining the data, and also then looking at the bathtub curve of hazard rate, and then understanding load strength and the impacts and how that links back to the bathtub curve. Okay, I hope you found that useful, and if you have any questions, just touch base with me. Thank you for listening.